So, I'd like to introduce our next two speakers who are going to do two for the price of one, tag team presentation. First, we have TVIW Organizing Committee member Dr. David Fields. He is a PhD, an experimental physicist formerly of Oak Ridge National Laboratories. He's the founder and president of Orion and the director of the Tamke-Allan Observatory, a private pilot, and a self-proclaimed gentleman farmer. Working with him, I'm pleased to announce that we have Dr. Paul Shuch. Paul, make sure we all know how to pronounce his name, so if you're in your guide here, if you forget, he says it rhymes with luck. And don't know if that fits his description of his career or not, but we will find out. He's a microwave engineer and the inventor of home satellite TV. He has a PhD in engineering from the University of California, Berkeley. He was the founder and began the SETI League. He became their first executive director, and he now holds that position as an emeritus. He is the principal investigator on the SETI League's Project Argus All-Sky Survey. First speaking will be David, followed up by Paul.
Okay. Frontiers of Radio Astronomy and SETI, they're both very interesting. And what we're going to cover is not always good news. We're going to cover the white hat and black hat aspects of what we're doing. Believe me, we really are. What we're going to do for development of tools. Tools are very important. We are explorers. A little louder. We are explorers. We are scientists. We try to have high, upscale, polite research. We try to do things the right way, but there are other aspects also. The tools are important. And what we're going for is sophisticated help, sophisticated software, sophisticated algorithmic development. There are applications of radio astronomy, and there will be in Interstellar. Now, first, since I'm an optimist first, the good news and bad news. The bad news is I don't think that we are going to boldly and bodily go to the stars. What we're going to do is start out. We're going to map the road. We'd like to go. We're going to start out. And we're going to try to do the right thing. We're going to try to explore. There are ways we can explore. The good news is we do have a ways to do it. And, of course, our research. The white hat part first, the good guy part first. We're physicists, we're scientists, we're teachers. We try to do the right thing. And we have coaxed, we have prodded, we have measured nature. We have got tools. We know our physics is the same as the physics out there. So in a sense, we're knowing what we're going to find. We're knowing the science. But there's more to it. What about the non-science? What about the intelligent part? Well, I'm going to turn that part over to Paul in a few minutes. It's a tool, and we're going to do that out there too. We're going to listen in. And I'm so proud we're going to do that. Hopefully we'll take our tools, just like we took our tools for space orbiting telescopes that were watching the Earth, but after about 20 of them, we turned one of them up and we called it the Hubble. So we're going to use these tools and listen in on what's out there. And both the good hat and the white hat and the black hat parts are going to move us ahead. So in radio astronomy, we've moved ahead. We've got all these signals coming in. The background is from John Krauss, one of John Krauss' excellent books on radio astronomy. There's a lot of stuff out there. This is the natural part, the natural signals. And we get spectral information and variations in time and polarization, power, just a lot of information. It gives us more and more understanding. In terms of the hardware, well, we started out 100 years ago with single component receivers. Hertz receiver was simple. We added to it, we invented more concepts. This is one of the early beautiful radio astronomy receivers. And the receivers grow in size and capability to the point is what we do now is software-defined radio. It's not just radio astronomy. If you reach in your pockets, your cell phone, it's a software-defined system. So a little group I'm with, and those of you that have been to TVIW before know about this, we started building a software-defined receiver for radio astronomers. And I'll show you one later. This is Raspberry, and it started out as a board. It started out as a thing we carry around in the suitcase back and forth to Atlanta, and it ends up with a little gadget up in the upper right. And it's not this side; it's this side. A little couple of 2-inch by 2-inch little boards stacked up, and it does good things. You can connect it to different antennas go up to 4 gigahertz, 20 megahertz, and images, well, yeah, if you really, really process, most of the time, whereas optical telescopes give us pretty pictures and tell us how the universe is. Radio telescopes tell us how the universe looks. Radio telescopes tell us what it is. Gives us a little more information. And sometimes they're just squiggly lines like this. Well, our software does an FFT on what's coming in and shows us the spectrum. So the little squiggly line at the bottom is the spectrum in the water hole frequency, the 1420 megahertz. So we're looking at a hydrogen cloud. This is atomic hydrogen, maybe 30,000 light years away. It's not a small cloud, it's a big cloud. Okay, so the little bump is what we're after. And we process it, it happens pretty quickly. We get something like, subtract the background, what you see on the upper left. And if we want to smooth it so we can more clearly see the self-absorption there with the hydrogen, you get what's on the bottom right. So we can connect this to different antennas and do a lot of things. That's the radio astronomy side of it. All the tools of radio astronomy, plus some others, can be applied to look at intelligent things. So I want to turn this over to the guy with the black hat. My colleague, Dr. Shuch.
So, you want to go to the stars someday?
Yes.
Why wait? We can do it right now, employing the photon, the fastest spaceship known to man. It travels relatively unimpeded through interstellar medium at the fastest speed that Einstein will allow. And that's what we'll be talking about next. A lot of what you're going to hear here comes from my recent book, Searching for Extraterrestrial Intelligence, published by Springer Verlag, a shameless plug, available on Amazon and wherever fine books are sold. And my subtitle, SETI Past, Present, and Future. I'll be talking a little bit about the past and present right now, and then in our C for Como breakout sessions later, we'll be talking about the future of the search for extraterrestrial intelligence. And it seeks to answer a fundamental question that has haunted humankind since first we realized that the points of light in the night sky are other suns. Are we alone? For the first time in human history, during the last century or last half century, we have developed the technology to seek a definitive answer. And that technology comes to us from the relatively young science of radio astronomy, discovered quite accidentally by Carl Jansky in the Bell Labs in the 1930s when he was trying to track down a source of interference to our transatlantic radiotelephonic communications. And he discovered that there was a source of noise in the sky, but it wasn't always in the same place at the same time, and it didn't track Earth's rotation. That noise repeated consistently every 23 hours and 56 minutes, which we now know is a sidereal day. So Jansky figured out the noise was coming from way beyond Earth. What he was detecting was the galactic center. And this was the birth of the science of radio astronomy, which almost died stillborn. Because once Jansky had solved the problems for the telephone company, he went on to other projects, and his work was almost forgotten, except by amateur radio operators. Greg Reber, W9GFZ, the ham radio operator in Wheaton, Illinois, who built this beautiful 12-foot diameter antenna in the backyard, 30-foot diameter antenna in the backyard of his mother's house. She was a school teacher and very tolerant of his pursuits. Grote was the father of observational radio astronomy in that he actually turned an observation into a science. He was the first to map the Milky Way galaxy. Of course, nobody would publish his work initially, because the signals that he was detecting were millions of times stronger than what theory said they allowed. And after all, he was just a radio engineer and a ham radio operator. What did he know about astronomy? So his work was almost lost. During the Second World War, it was unearthed from the slush pile of a publisher's stack in his desk because Astrophysical Journal had no articles to publish. Everything that everybody in physics was doing was classified. And the editor said, damned if I'm going to publish an empty journal, I'll put this in, nobody's going to read it anyway. That was the birth of radio astronomy. The man to turn toward the search for intelligent signals in space was Frank Drake, a young recent graduate from Harvard. The ink on his diploma was as wet as he was behind the ears when 29-year-old Frank took a job at the newly founded National Radio Astronomy Observatory, NRAO, Green Bank, West Virginia. And while there, he got permission from the director of NRAO, Otto Struve, to use one of the antennas there, the 85-foot diameter Howard Tatel telescope, in his spare time off duty to search for signals from other intelligent species in the cosmos. Only Otto Struve said, keep it really quiet, keep it on the down low, because we don't want anybody to know that we're using a government facility to search for little green men. That would be professional suicide to admit that. So Drake kept it all to himself. And then the Kokonian-Morrison article came out, a short 3-page letter in Nature magazine blew the lid away because 2 Cornell professors were proposing to do exactly the experiment that Frank Drake was actually doing. Neither knew anything about the other. This is a prime example of what I call the parenthood principle. When a great idea is ready to be born, it goes out in search of a parent. Sometimes it finds more than one. So now Schrodinger's cat is out of the bag, and Frank had to go public with, by the way, it's a great paper, a good article, nice proposal, and incidentally, that's exactly what I'm doing right now. So for a few short weeks in April and May of 1960, Frank Drake performed the very first observational SETI experiment. And he made a momentous discovery which he couldn't publish. Frank discovered the U-2 aircraft. But he couldn't say so because he turned his when he slewed his antenna the very first time from Tau Ceti to Epsilon Eridani, he got a strong periodic pulsing signal, loud, clear, and unmistakably intelligent. The next day he was ready when it repeated 23 hours and 56 minutes later, and he had a second antenna from which he was able to determine this signal was not coming from Earth, but it was not coming from very far away either. It was coming from maybe 80,000 feet away, and that sounded like an aircraft except for one little problem. In April of 1960, no such aircraft existed that could fly at 80,000 feet. It didn't exist until May 1st when the U-2 was suddenly upon us, when Powers was shot down in one. So Frank had a pretty good idea what he was detecting, but wasn't able to say so. However, Kokonian-Morrison laid out exactly the frequencies, the strategies, the star targets, everything that Drake had already independently arrived at. And Frank was also the father of the famous Drake equation. Just 1 year later, the world's first SETI scientific meeting was held at Green Bank. It was a 1 week-long meeting attended by only a dozen people, people whose names became household words eventually. There was a young postdoc working on a split assignment between Berkeley and Stanford, who had just finished his PhD at the University of Chicago on thermal runaway on Venus. He was the first person to figure out the greenhouse effect on Venus from Earth observations only. We didn't have any Venus spacecraft then. And young Carl Sagan, of course, wowed the world with these ridiculous suggestions that maybe other stars might have habitable planets. And he had the gall to say so, and he went to this first SETI meeting that Frank Drake hosted, and as a consequence, he did not get tenure at Berkeley. However, while at Green Bank, he did meet Phil Morrison, who was at Cornell, and Phil managed to make sure he got a job teaching at Cornell, where he stayed for the rest of his career. 7 days of meeting and an agenda, one item to discuss each day. The first day, stellar astronomy. The second day, planetary science, this new science that Carl Sagan was pioneering. The next day after that, they were going to talk about Earth-like planets, the Goldilocks zone. And day 4 was going to be about the evolution of life. Day 5 about the evolution of intelligence. Day 6 dealing with communications technology. And day 7 was going to be the sociological implications of technology, the longevity of a technological civilization in its communicative phase. Bear in mind, this was 1961, the depths of the Cold War, right around the time of the Cuban Missile Crisis. We're talking about a time that our own longevity was highly in question. And then Frank did something whimsical. He put the agenda on the board, 7 items, 1 per day, and then he strung them together into an equation, put an n equals in front of them and said, if we know all 7 of these things, we can calculate the number of other communicative civilizations at our technological level in the Milky Way galaxy. Only one problem. Of those 7 things that he tried to quantify, we only knew one of them, the rate of stellar formation. Everything else was speculative. In the decades since, we've picked away from left to right at the other factors in the Drake equation. We now know something about the formation of planets and the prevalence of Earth-like planets. So we're down to 1, 2, and 3. We've got life, intelligence, communications, longevity. We still don't know. So the Drake equation, which is the fundamental equation for estimating SETI probabilities, remains an elegant tool for quantifying our ignorance. There followed a number of interesting SETI experiments. I can only touch upon a couple. Big Ear Radio Telescope, Von Krause's beautiful design at The Ohio State University. It no longer exists. This telescope is now a commercial golf course. You see, in 1968 through 1997, there were 50 golf courses and 1 radio telescope in the state of Ohio. Now there are 51 golf courses. This is the direction that intelligence takes us. And it was here at Big Ear, that the SETI enterprise received its most promising, most tantalizing, most elusive candidate signal ever, the so-called Ohio State University WOW signal, so named because my colleague Jerry Eman, who saw the computer printout, scribbled 1 word in the margin of the printout, and it's a good thing he didn't write what he was really thinking. If he had, we would be talking today about the Ohio State holy shit signal. But Jerry is a quiet and reserved guy. He kind of kept that to himself. Nevertheless, tantalizing because it had all the fingerprints of extraterrestrial intelligence. Frustrating because it never repeated. And we have a basic law in statistics. When n equals 1, all bets are off. I mean, how do you do the mean, median, and mode and standard deviation of a single number? You can't. So until it repeats, it didn't happen. And this is the big frustration for SETI science. We have to find a way to get independent verification of what we see or what we think we see. One way to do that is with huge arrays of multiple dishes. This was the Cyclops proposal from NASA Ames in 1972. It was to have been 900 dishes, 100 meters each in diameter, working as a phased array. We're talking about the greatest radio telescope never built, because its price would have quickly exceeded the gross planetary product. Nevertheless, it resulted in the publication of the Cyclops Report, a book that NASA published, 10,000 copies only, and they went to the 10,000 electrical and mechanical engineers most interested in developing large arrays, and became the Bible for how you would do a large system design on the scale that we would never be able to accomplish. But most of us, and I was a grad student at the time, most of us in the enterprise today cut our teeth on the SETI book, the Cyclops Report. My organization, the SETI League, one of our first technical projects was to republish this book so that it is still available to you all. You can purchase it on the web. Look at www.setileague.org. And for a modest $20 contribution, which includes postage, you can have a reprint of the original Cyclops Report, and you can study it yourself. Arecibo, the greatest radio telescope in the world, the largest single-dish antenna radio telescope, the most sensitive radio telescope, has been used for observation. In our C for Como breakout sessions, I will explain to those of you who attend why Arecibo is not the ultimate SETI telescope, however. Nevertheless, it's been an interesting place to do observations. Frank Drake went from Green Bank to become the director of Arecibo earlier in his career. He also did a lot of work with pulsars, which, by the way, when they were first detected in 1968, Jocelyn Bell then, later Jocelyn Burnell, and her advisor, Anthony Hewish, jokingly referred to these periodic pulses as LGMs. They labeled the two that she detected, LGM1 and LGM2, and that, of course, stood for Little Green Man. They didn't believe that, but it made for an interesting conversation at Cambridge. Anyway, at Arecibo, we've also done what we call active SETI, or METI, messaging to extraterrestrial intelligence, where we've actually sent up signals which were not ever intended for detection by extraterrestrials. The Arecibo message in 1974 was more or less a publicity stunt as part of the rededication of the telescope after its new surface was added. And the surface makes it really pretty, viewed from Google Earth, by the way. The Arecibo message, designed again jointly by Frank Drake and Carl Sagan. You see, it's a small family of people who got involved early on and stayed involved and stayed connected. And the Arecibo message beamed at a cluster of stars 58,000 light years away, so you have to wait 116,000 years for an answer. This was not an attempt at communication, it was an attempt at demonstrating feasibility. If we can do it, the reasoning went, so can they. John Billingham was the head of the very short-lived NASA SETI office at Mountain View, California, NASA Ames Research Center. John was a medical doctor, a flight surgeon who got involved in astronautics biology early on. He was actually the physician to the early astronauts and went from there to opening a life sciences division for NASA at the Ames Research Center in California. And it was JB, who sadly passed away just a few years ago. It was JB who decided that SETI was a credible pursuit within NASA and worked long and hard to create and obtain funding for a NASA SETI project. It was modestly funded. The NASA SETI office was budgeted at 5 cents per US citizen per year, quite literally pocket change. And they were authorized to do a 10-year two-pronged search for intelligent signals from beyond. Over 10 years, they were going to cover the 1,000 nearest sun-like stars to reasonable sensitivity and the whole rest of the sky to lesser sensitivity, looking for artifacts that could not be produced by nature under the laws of nature as we understand them. 1 year into their 10-year search, just as they were beginning to spool up, Congress pulled the plug. A senator from the state of Nevada, Bryan, said, "We've been looking for a whole year. We've spent millions of dollars, and not one single little green man has stepped forward saying, 'Take me to your leader.' This proves," said Senator Bryan, "that they are not there." Well, actually, all Senator Bryan proved is a hypothesis that many of us had long held, but we now have experimental evidence to support the hypothesis that there is no intelligent life in Washington. One of the best things that happened after NASA SETI died is John collaborated with Tom Pearson, an administrator from academia who knew how to organize with low administrative overhead. And they put together a nonprofit organization, my sister organization, the SETI Institute in Mountain View, California. Basically, all the NASA SETI scientists, when they were fired, walked across the street, regrouped under private funding and under Tom's leadership, and formed an organization that strove to keep SETI science alive. They took over the targeted search, that list of 1,000 nearby sun-like stars that were believed to probably have planets. Remember, this is before we had detected exoplanets, so we were only guessing. But they guessed really well, because that list of 1,000 stars, most of them are now on the exoplanet list. So they did a pretty good job figuring where the planets should be. And over the next 9 years, Tom and his group completed the targeted search aspect of SETI. They did so under the banner of Project Phoenix, saying that they rose from the ashes of NASA SETI's demise. But that's only one of those two prongs. The other prong of NASA SETI was the all-sky survey. You see, if you guess right which stars to look at, you can hit pay dirt really quickly. But what if you guessed wrong? There could be another star right next door to the one you looked at, and that's where a signal is emanating, and you'll never see it. So that's where the all-sky survey came in. And when the SETI Institute took over the targeted search, I helped to found the SETI League. I'm wearing the billboard here. Another private nonprofit organization for the purpose of taking over that other prong of the SETI search, the all-sky survey. Now, SETI League was founded as a ham radio club mainly, microwave enthusiasts all over the world, grassroots, global, and we gathered together and had meetings and did design work, and we figured we could come up with our own low-cost radio telescopes capable of continuing the all-sky survey. So I designed a system. As was mentioned in my intro, I actually ran the Silicon Valley startup that developed the world's first home satellite TV receiver, so this was familiar ground for me. We took some of our big ugly dishes from the backyard that had been used for satellite TV, and we took some of our microwave receivers and tweaked them just a little bit, and suddenly we had a low-cost radio telescope design, which we published. I'm a big believer in open source. This is all freeware. It's all out on the web. Patents only serve to make only serve to make patent attorneys wealthy. They don't help inventors anyway, so why bother to patent it? You know, a patent, what it does, it gives you the right to litigate when, not if, but when somebody infringes. So all this design, I published it, put it on the web, on this new thing called the World Wide Web that we had, and suddenly everybody was building radio telescopes and they looked like this. And the goal was 5,000 of them around the world, looking in all directions at once, so that next wow signal that falls upon friendly shores will be detected and verified. That was the concept. And then the global recession hit. We never got to 5,000 stations. We got to 127, and then everything stagnated. And that's the status of SETI right now. There are some other efforts going on. Our friends at the SETI Institute have been working on their Allen telescope array, planned as an array of something on the order of 300 6-meter dishes, funded, budgeted at $25 million, most of which was being contributed by some deep pockets people whose names are now household words, one of whom was the co-founder of Microsoft, the other was Microsoft's chief technology officer. And they did a fine design job. My old grad school advisor, Jack Welch, was the chief engineer on it. And the result was they burned through 50 million of those $25 million, and they have 42 dishes on the air. Everything costs more and takes longer than you think it's going to. So I will close with the last comment from the original Cocconi and Morrison article. The reader may seek to consign these speculations wholly to the domain of science fiction. Well, I'm a sci-fi enthusiast. I think that's great. And then he went on to say, Morrison went on to say, the probability of success is difficult to estimate, but if we never search, the chance of success is 0. Thank you.
And we have time for a couple of questions. Wait on the microphone, please. I've lost my runners. Drew, can you take care of running the mic to the speakers? Thank you. The questioners, we have one back there.
I know you.
First, let me thank you. Okay. Let me thank you for a very nice historical perspective, which is all true, I think. And you and I shared the same graduate advisor at Berkeley, and so you won't mind if I criticize. The point I'd like to make is that everything you've said is predicated on the signal being an RF signal in the microwave band, and that's a very old assumption. I made the case a long time ago for resurrecting lasers as a signal to take seriously, and I still believe it. But if you back off and look at what's happened here on the Earth, we're rapidly moving away from broadcasting anything into surrounding space, and if we don't have a motive for the signal identifying ourselves, then there's nothing there. And yet, we begin to take seriously the threat of near-Earth objects colliding with the Earth, and that entails the use of advanced radars to give advanced detection capability. And there may be solar systems where that situation exists in spades, and so we have to look to the question of, can we identify radar signals that are being broadcast around that might be the ticket rather than an intelligent signal directed to us.
John, thank you very much. You've just given the presentation I was going to give in the C4COMO session, so I could go back to Pennsylvania now.
No.
Okay, 3 points in there. 1, lasers. Absolutely, yes. I'm a microwave engineer. At Penn State, they brought me in 25 years ago to start a fiber optics lab. What did I know about fiber optics? Well, it's really easy. It's microwave with very, very small waveguide and very, very high frequency, but it's all the same technology, and absolutely we're looking for coherent laser signals as well. The Project Argus search that I head up is a microwave-based search because that technology is cheap and it's out there and the amateurs have it already. Lasers, absolutely we're working on optical SETI as well, and that is probably our future direction. Point 2, the Earth becoming microwave quiet. Absolutely true. We have taken down all of our over-the-horizon Cold War search radars, and that means since we decide to wage peace, we've become less visible to our neighbors, and that means we must hope that our cosmic companions continue their Cold War a little longer if we want to detect them. Or near-Earth asteroid risk. There's absolutely no reason we should not be using active bistatic radar systems to monitor near-Earth potential threats. And those signatures will be easily visible to our existing radio telescopes. So if other planets have planetary protection, we have a shot at detecting them.
That's all we have time for. Thank you very much.